What were we talking about last time?
ZPE.
Yep, we talked about 0-point energy and what that meant. So if we plotted that out, and about how these rungs are different for the harmonic, or they're spaced evenly for the harmonic oscillator. What was the smallest value of n we could have for the harmonic oscillator?
0.
Yep. And is equal to 3, I'm quitting at that point, and then the distance between these two things, what was it?
1. Or is that the ZPE?
No, it's like.
Nope, the ZPE was actually this part down here.
Oh, it's 1 lambda H.
Yeah.
Or new H.
Was it 1 or was it 1/2?
1.
Okay. Yeah. Because this would have been 1/2 H nu. This one would have been 3/2 H nu, 5/2 H nu, and so on. Yep. Okay. So we talked about how it has even spacing and what the 0-point energy actually is. Do you guys still feel like you understand what the 0-point energy is, or not really? I saw 1 head nod and 2 not head nods. So, Lily, can you talk to me about what that is, or give me an idea?
It's like the correction for like, because we can't say that there's no movement at 0 Kelvin, so it's like the correction to fix that if we have like, I don't know exactly,
Yeah.
but like it's a correction to fix that assumption.
Yeah, exactly. So if when we look at a potential energy surface, we would say that this is the minimum, but it actually can't be, even at 0K, like you were saying. What does this account for? What principle is it trying to correct everything for?
The Heisenberg uncertainty.
Yeah, the Heisenberg uncertainty principle, where the change in position, or excuse me, the uncertainty in position and momentum had to be greater than that, right? So even if you have everything at 0 Kelvin, it doesn't mean you're going to just boop, end up there, because then you know where the electron is, and then the momentum will shoot through the roof. So you're exactly right. It's like a correction. Okay. That's one thing we talked about. What was the other thing we talked about? Or started getting into?
Power functions.
Can you say that one more time?
We did power functions.
Yeah, so we started looking at power series in our wave functions, right?
Oh yeah, power
So-
series, not power functions.
Yeah.
Sorry.
I like power functions. I think it sounds cool. I like power series too. I don't know why they were called that name at all, but because it's raised to a certain power, maybe. I don't know. Were you guys probably never watched Power Rangers, right? Oh, did you watch Power Rangers? Was it like that was like the coolest thing when I was like 5 years old? Every time I hear Power Series, I think of Power Rangers. I don't know why. What was special about the wave functions of the harmonic oscillator?
It was different for even and odd.
Yep, it was different for even and odd. So the generic wave function for these guys is e to the negative of x squared times f of x. This thing always gets incorporated, and what was this f of x again?
The power series.
Yeah, this is the power series. And Ellen, you said that we had to keep track of if it was even or odd. So we had f of x of an even function. What's the lowest index we could have for an even function?
0.
Yeah, so it's weird, 0 is even. In this case, we go to infinity for even. That, and then we would have one for odd That's the exact same thing, except where does our index start?
1.
Yep. Okay, and we went through a couple of wave functions. What would, where n is equal to 1, what would that wave function be? Or I'm sorry, 0. Sorry.
So
E to the what?
negative alpha x squared over 2.
Yep.
And then c sub 0.
Yep, because we're just looking at that first term, x to the power of 0, 1, we're good there. Then, for n is equal to 1, we still have this e to the negative alpha x squared over 2 times what?
c1x.
Yep. C1x. 2, keep that e to the alpha x squared over 2 times, what would that one look like?
C sub 0
Yep.
plus C sub 2 x squared.
Yep. We'll do 3, and we'll be done after that one. E to the negative alpha x squared over 2 times what?
E c1x plus c3x to the 3rd.
Yep. So you feel like you got it. Okay. So these wave functions right now are all unnormalized. How do you know that they're not normalized? What gives them? Yeah.
No constant.
Yeah, no constant out front. If you see no constant out front, generally that means it's not normalized, so we have to normalize it. So, we need normalize these functions. Get the normalization constant. Okay, we're going to look at the most simple one. And then we're going to just kind of jump to some math and some complex mathematics. So this is basically your answer to the very last question on the Quizlet. What is the normalized wave function, harmonic should be more formal and say a quantum harmonic oscillator. Be lazy. I gotta turn my alarm on so I don't talk forever. Yeah, there we go. Yep. Okay. What is the generic formula for normalization? Yeah. 1 is equal to what?
An interval. And then you have n squared, and then the so psi of the, oh my gosh, the complex conjugate of
There you
psi, and then normal psi, and then d tau.
Yeah, we'll go with d tau. And then where are the integration limits for this system?
Negative infinity to infinity.
Yep.
complex conjugate.
I couldn't
Like-
remember the word.
I do that all the time. There's like probably like what, maybe 1% of the population knows what a complex conjugate is, so. Okay. We need a subscript down here. Oh, I didn't say which one. Sign up. There we go, problem solved. Okay. We can plug in for some stuff here. We can pull that normalization constant out. Negative infinity. We got to start plugging in values here. What does psi naught look like again?
E to the negative alpha x squared over 2.
Yeah. What's this thing?
A constant.
It's a constant. Huh. Do we have to really incorporate it into our psi here? Why not?
Just need one out of the interval.
Yeah, exactly. This c sub 0 will actually just become our normalization constant. So we can ignore that part of the wave function for now and just plug that in. So let's do that. We get e to the negative alpha x squared over 2. If I take the complex conjugate of that, does anything change? Right? Because there's no i's. And then what does my integration parameter become? D.
dx.
Yep. Okay, simplify that a bit further for me. So multiply those two things together, what do we get?
E to the negative alpha x squared.
Yep. So when you were saying to yourself, why the hell do we have this divided by 2 here? That's just annoying. Not very annoying when you start looking at operators or trying to get densities, because now we just have e to the alpha x squared, right? Okay, but now am I forgetting a minus sign? Shouldn't be. -1 times -1 is still. I am forgetting a minus sign. I'm sorry. You don't multiply those
You add
together. You add them. There we go. Algebra. Okay. Trouble becomes, you look at the table of integrals, you have certain integration limits and you can't really go past those. And the one that we have, I think, was e to the negative bx squared dx is equal to like that, right? So now what are we gonna do if we have this one, but our integration rates don't match?
We can split the interval.
Yep, we can make a match. We gotta try to. Okay. This is a symmetric function. Do you guys know what I mean by a symmetric function?
It's the same like in the negatives as it is the problem.
Yeah.
Yeah, exactly. So if you have x along here, and let's say it looks like that, that's a symmetric function about 0. So really, you could take the integral of the yellow side and of the blue side, or what else could you do?
2 times one of the sides.
Yeah, you can do 2 times this side or 2 times that side, and it's going to get you the exact same answer. So that's what we're gonna utilize here. So ln's right, we pull out a 2. What's our integration limit become in that case?
0 something.
Yep. Do we have to go to infinity? Could we have done 0 to negative infinity? Yeah, we could have, but then we'd probably have to find a more complicated integral. Okay. Then we got e to the negative alpha x squared dx. We integrate that thing. What am I going to get out after I integrate?
1/2 square root of 5 over alpha.
Yep. Okay, simplify that a bit further for me.
N squared, square root of 5 alpha.
Yep. Oops, alpha 9. And what's that all equal to?
1.
Okay, so what are we trying to find here?
The n.
Yep. So let's shuffle that thing over to the other side. We get alpha pi to the 1/2 is equal to n squared. What's n going to be equal to then?
Alpha over pi.
Mm-hmm.
Or wait, no.
To what power?
That's like, oh, what? 1/4?
Yep. There we go. So therefore, our normalized wave function is that. Okay, so that's for the simplest spot. It's kind of nice because it already has that the normalization constant kind of hidden in there. But what about for all of these other guys? We're not going to go through each one and show this, but there's a pattern that ends up happening thanks to this power series. And you can show that the wave functions for the harmonic oscillator can be expressed in the following fashion. So, it can be shown wave functions harmonic oscillator follow the pattern. N is equal to pi over 4 over 2 the n times n factorial to the 1/2 n Okay. A lot of scrambling down. Factorials. Do you remember what a factorial is? So if I have 3 factorial, what is it?
3 times 2.
Yep. Total how much?
6.
Yeah. Okay. This other thing. This is a function that depends on alpha to the 1/2 and x times x. This is known as our Hermite polynomial. There are special class of functions that show up in mathematics, and mathematicians get really excited about it. We'll talk about what they are in a second. Seeing how much math we want to go into with that. Okay. So that thing is a Hermite polynomial. It's something you can just look up and plug in values for. For convenience, a lot of times, we're going to say h sub n, L x is equal to h sub n to this fancy e. Wow. All right, we did it. There we go. I don't remember the parentheses. There we go. Where our fancy e, it's gotten tremendously worse, is equal to alpha 1 half x. If you see a scribble up on the board and you have no idea what the hell it is, it's probably this thing. If you can't identify what it is, point it out. Maybe I'll just use a different color, because that's pretty fast. So these are a set of mathematical functions that are named after Charles Hermite, because he developed a paper in 1864, but they were originally defined by Perry Simon Laplace. Have you guys talked about Laplacians, or in your philosophy classes talked about Laplace's demon? Okay, this is an interesting philosophical question. So Laplace was this mathematician and this philosopher, and he thought about, well, what happens if we create something that has all knowledge in it? So he proposed a demon. People are starting to think, this is way closer to AI right now, or what AI will become. And so to something that knows everything, it could calculate like when, I don't know, when you're gonna die, or how your car will break down. It knows everything. If it knows everything, time will just look like a continuum to it, because it will know everything that's going to happen. Mm-hmm. So, kind of a weird philosophy. Have you ever, I don't know, The Watchmen was like a really big show or movie when I was going to college. Did you guys ever watch that one? Like Dr. Manhattan. Alright, don't worry about it. If you're bored sometime, watch it. With that character yourself, it's the same thing. Okay, so let's talk about these Hermite polynomials really quick and see how we can use them. I'm glad some nerd worked on them in the past, so we really don't have to, because defining them is really painful. I'm sure Dr. Hansen, if you went up to him, he is probably making his class define all this crap. I'm not going to write down any of the historical stuff. So what they are, the polynomials show up in quantum. And they're orthogonal polynomials. Which is extremely beneficial to us. If you're
remember what the word orthogonal means again?
0 or 1.
Yes, exactly. That's nice. If they're not the same function, the result is 0. So that can benefit us greatly when we're talking about these systems. Okay. The Hermite polynomials. Are solutions to the differential equation h sub n double prime minus 2 fancy h sub n prime plus 2n h sub n is all equal to 0. Okay, what do the primes mean again? Yep, they're derivatives. The other thing is they satisfy the following recursion relationship. Spelled recursion and satisfy. Anyways, h sub 1, 2, h sub 1. Where remember recursion relationships, if we know a couple of things in here, we know all the things in here. It's a pattern that just keeps happening over and over and over again. Okay, you can write these down if you want to, you don't have to, they will be provided for you on every Quizlet from here on out. Okay? It's worthwhile, if you want me to, I can put the sheet up on the internet for you. I don't know if I already did or not on Google, but it's a worthwhile thing to have. I'm going to make a little table that's going to be about half of a page. And maybe not, maybe I'll quit halfway through. Okay, so we have some value of n, so this is our principal quantum number. And then we have, what does the Hermite polynomial look like? I want to get to at least 4, because it starts getting more complicated at that point. N is equal to 0. So if you look back at your generic expression, what is the value of that polynomial? Not 0, because then the wave function would be 0. It's almost, if it's not 0, it's probably, yeah, it's a quantum class. Okay, the 1, it's 2 fancy E. That's bad, whatever. For 2, it's 4 epsilon squared minus 2. For 3, it's 8. Oh no, let's try that again. Epsilon to the 3rd minus 12. For 4, it's epsilon to the 4th minus 8. Epsilon to the 2nd, it's 12, and then there's a handful more that I'm going to spare you writing down. Okay,
What do you notice as we increase our value of n?
Gets more complicated.
Yeah, it gets more complicated. It gets tougher. Okay. The other thing is for our wave function, we've defined everything in terms of alpha and x, but for the Hermite polynomials, we have this fancy e which combines the two. So how do we actually use this information with a wave function? So let's try to normalize psi sub 1 for our harmonic oscillator, and we'll see how can we just incorporate this in and utilize the Hermite polynomials. So, sample. Normalize psi sub 1 for a harmonic. So generic expression for normalization, 1 is equal to what?
N squared.
Yep. N squared, integral, going from negative infinity to positive infinity. What else do we have in this thing?
Wavefunctions.
Yep.
And then derivative detail.
Yep. Okay, in this case, we have psi sub 1. Psi sub 1. Look back at the expression I said that shows the pattern associated with the harmonic oscillators. Tell me what the wave function is.
The e to the negative alpha x squared over 2 times.
That thing. And then we got 1 over 2 to the power of 1 times 1 factorial raised to the 1/2. What else do we got?
This one.
Oh, we'll leave H as generic right now.
HN.
Yep, so H
and
what?
1.
Yep. And at this point, it depends on alpha and x. And then we have e to the negative what?
Alpha x squared.
Yep. Okay, this is the normalized wave function. So we already know our answer, which is good. What's all of this stuff?
The constant.
Yeah. That's actually n. So we need to normalize this thing. We're going to pretend we don't know this, but we do know this other portion. Okay. So now, what we want to do next, we'll plug all this junk in. H sub 1, x, squared over 2, H sub 1, minus alpha x squared over 2 dx. Okay, the next thing we need to do is we have everything defined through epsilon here. So we gotta convert this into this epsilon thing. So what we're going to do is we're gonna sub this, and what's epsilon equal to in this case?
Alpha 1.
Yep. And d epsilon into the equation. And squared this. E to the negative epsilon squared over 2. God, you can pick a messier thing. And then, since this was dx, if we want to transform it into d epsilon, we have to divide by output of 1/2. Okay. We can pull out some things and we can rearrange.